we're talking about resilience for critical infrastructure. This talk is going to be more about what to do in the event that there is a problem. And it's some about engineering for the problem, what to do through the problem, how to make the problem less of a problem. Who am I? Why should you listen to me? I'm president and CEO of a consulting firm. 35 years in critical infrastructure. I'm old enough to remember when we had analog control systems, like pneumatic control systems and old school copper, for example. I've been in various different industries. I've worked as an asset owner in electric, water, and telecom space. I do actually know how to climb poles and run old school copper wire, for example. I was one of the architects of NERC-CIP, which is a US regulation on critical infrastructure, electric power in particular. We started writing this back in 2002. Some of you probably weren't born yet. I was the first regulator for NERC-CIP in the US, so I actually helped get this off the ground. I know what it's like to actually try to move a continent-wide system into a regulatory structure, which is not easy. I've taught for SANS, I've taught for Energy Sec, I've taught for CISL in Copenhagen, and then I also do some work in Spain, and I do lots of advisory for boards, manufacturers, vendors, governments, asset owners, you name it. Okay, today we're talking about modern OT systems. They're reliable in design, but they don't scale. The bigger you make an OT system, the more it becomes dependent on the automation, and it becomes brittle, and it becomes fragile. So when you look at automation systems, the smaller they are, the easier they are to actually keep contained and keep reliable. So you have to think about that when you're designing resilience in your systems. Resilience itself doesn't scale well. It has to be more compartmentalized. So recent events that we've seen, these are global events, have shown a lot of the same failure modes, and we'll talk about those. The adversaries, there's been a lot of different discussions around adversaries so far. They don't just break into the system anymore. They get in and they hide for a while. Now they're just getting in, hiding. They'll wait for the right time, and then they'll destroy everything. It's not like ransomware. Ransomware still does exist, and they will, take your data and extort money from you. But now adversaries, especially Russia in particular, will just burn the place down. There's discussion around, should we just replace the technology? You can't do that. You can't afford that. It doesn't make sense. You would take the system down to prevent the outage of the system. You're creating an outage to prevent an outage. You've got to find a way to do this with the existing technology in place. So there are some engineering methods that you can use that will actually minimize this and contain the failure regardless of whatever the event is, whether it's storms, squirrels, or hackers. It doesn't matter. At the end of the day, the goal is to basically, whatever the trigger is, storm, wipers, anything like that, that you can still continue operating in some way. Maybe it's not perfect, but you can continue operating, right? So the threat environment, I picked this particular area for the threat environment. Russia attributed some destructive operations all across the NATO neighbors. Estonian foreign intelligence, no military attack in 26 or 27, but we are seeing a lot of hybrid attacks right now already. They've increased in very significant numbers, as you can see as we go through this slide deck. These statistics are frankly frightening. This is not good. This is a graph that goes like this. This isn't some steady climb. This is a spike. That's significant. Not only is the spike significant, but the fact that this is becoming normalized. This is what we expect. This is now an everyday thing. That problem is even bigger. So, there's been a lot of talk about artificial intelligence. We opened up the conference with artificial intelligence. I'd like to at least get a little bit of level set with this. Let's be clear, your adversaries do have hacking tools. They have custom hacking tools. All the awesome tools that you've seen that you would want to use for defense, they have them for offense. They have adversarial tools, and they're actually extremely good. And those tools are not just one. You saw like the scaffolding and the agents and the combination of the agents with the models. They have that, as many of them as they want. They're not dealing with purchasing tokens. They have three things you don't. They have people, they have money, and they have time. That is something that is no one in this room typically has all three of those things. The time to exploit, the last stats I could get before I delivered this presentation this morning was under 20 hours, in some cases as low as 10. What does that mean? Pick a vendor, Microsoft, Oracle, doesn't matter. When they release a vulnerability, there's not a 0 day, right? Okay, this is the new vulnerability, we're gonna patch it. When that notice comes out, it can be as close as 10 hours before they can use AI to reverse engineer that and create a proof of concept exploit. So just notice of the vulnerability alone, and those details are enough for an AI to create an exploit within typically under 20 hours guaranteed, but within about 10 at this point. The next piece is, you've heard about Mythos, you've heard about Daybreak and OpenAI's option, all of these new things. There's actually a bunch of just open source models that you can use as well. There's a couple of research that have done something like basically just give the AI a notepad to work with. Just enable the AI a little bit more, and they can do the same thing that Mythos can do. All vulnerabilities can be discovered, every one of them, even closed source. Okay? Just accept that. That is now like the norm. So when you combine things like open source intelligence, what I can get just from general internet intelligence, you combine a bunch of technical data, the manuals, because I can pull in all the technical manuals. I can pull in every technical manual for that model since it was made, and I can see the technology trajectory of that platform. I can see where originally the source code was taken from, like open source projects, and embedded into the tool now. I can get all of that history. Then my dwell time inside your environment, so I understand your environment as well. I've got all the data I need about your tech. I've got all the open source intelligence. And you combine that with a really skilled human that's using a really good adversarial AI, and that is an incredibly powerful set of tools. It's very challenging to compete against. What you can also do with this is I can take multiple different infrastructures. I can take telecom, electric, gas, water, chemical, mining, manufacturing, and where they all intersect. That's really hard to understand how they all intersect with each other, but I can model this with AI, and I can find out how to intentionally create dependencies between these environments and basically make a very bad day on purpose. Just because I can model all of these pieces together and find out what's the worst possible scenario, create that scenario with AI, and then attack in that specific window to cause a much bigger problem. So you can actually create the worst possible situation with the technology we have right now. So the assumption I want you to come away with is basically everything is a contested environment. Assume that you are breached, and then operate as though you are. Because it's not, yes, you should still do prevention. That's just understand that. Yes, you should still do prevention. That doesn't mean that's all you do. You now actually operate as though prevention has failed, just in case. So we did this for about 30 years or so with IT, with OT, as we began to introduce IT into our world. We basically built these systems with the boundary and said, we're good, just don't touch anything on the inside. Well, the attackers are now definitely inside. We've got everything from VPNs. We just saw a presentation from Marchen yesterday about the modems that were basically on the internal backhaul for the environments. Basically, we don't have much of a perimeter anymore, despite what we think. And I'm glad we've at least gotten away from using the term air gap, because those just don't exist anymore. We've got supply chain issues. Firmwares are now vectors, OEM updates, pretty much anything that they can do to get bad code into your environment, they can do that now, even if it's paying a human off. Some of the stats I saw this week were around 1 in 8 humans will take a payment to introduce malware into your environment. 1 in 8. How many people work in your company? 1 in 8 will take a payment to introduce malware. So the environment itself is hostile. Things like GPS jamming, RF interference. You're near a war zone, right? These are things that are common now in modern warfare. So you have to behave like the adversary is already inside your walls, because in many cases they are. So the new operating assumption, how do you take your environment that we've spent many years connecting and creating other connections to other networks? Most OT operations today cannot operate without their data. They cannot operate without their technology. That data has to come out of the OT environment. It gets sent into various different places for analytics. You're bringing data in. Let's say you're a power system or some other area where like weather data has to come in because it affects your operations. So there's this steady flow of data in and out of your environment. What if you just basically cut that off? Could you operate? That's the question. Colonial Pipeline in the US is a good example. They had ransomware in their IT. They weren't sure how it was going to affect their OT. So as a precaution, just in case, they shut down their OT. So the question now is, how do you take your existing environment, or maybe you're lucky enough to have a greenfield environment. How do you take that and design it so that you can isolate it and still run? That doesn't mean cut off things like field telemetry to SCADA, for example, but it does mean cut off things like business partnerships and other connections. It does mean other external connections that you absolutely do not need. How do you know that? Have you tested? Could you operate in what we call turtle mode? When the danger is there, you close the shell and you wait. And when things are good, you peek out. Is it okay? Then you can come out of the shell again. So this is the new operating assumption. This is a document from CISA. It's just happens to be one of the latest ones. And CISA did base their research on the 25th of December Poland event. It's also in concert with Australia, UK, Canada, so many other governments around the world have all endorsed this same model for critical infrastructure: is shut down everything else and continue to operate. This is what we are trying to get to. This is our goal. So the trust map we have right now, I've got this nifty grid here, the trust that we extend out, what that trust actually allows, and then what happens when that fails, right? So you can see we've got things like default vendor accounts. Those can give you full device control, but often with undocumented capabilities, because as much as I love vendors, they just don't write everything down in the manual that the vendor accounts can do. And then, of course, 2025, Poland, 30+ facilities were compromised because of this. So you can see across these rows, these are typical things that we do, just part of our practice in OT. This is the trust failure problem that comes with these things. We have to find ways to get around this. And it's not just buy more technology. That isn't necessarily the solution. So you get 4 properties, what I call survivable systems. This is how the system keeps running even when it's under attack, under active attack. Now, when you look at these 4 things, these are 4 things you would normally do just to keep a good operation running. Don't think of it that way. First of all, yes, think of it that way, but also think of it while it's currently being attacked. Like you have an active adversary in your environment trying to make your day bad. Containable, visible, recoverable, and failback safe. If you read the text in there, each one of these is not just how do you do this to keep your operation and make your operation better, but this is how to do it when your operation is actively being attacked. This is how to do it when the adversary is trying to make your day bad. So basically, failure stays where it started. You contain the problem. You contain the adversary into the smallest possible environment. Trap them there. How do you get visibility? This isn't just visibility to make sure the operation is doing what you're doing, or detection that maybe you can see them, but this is how do you maintain visibility when the active adversary is trying to take away your visibility? How do you keep that? For example, something as simple as a tap that feeds telemetry out, and you get a copy of that data so the adversary can't go erase everything. It's sent out into a separate network. These things aren't necessarily difficult to do, but we don't think about them because we haven't been under attack in this situation. Recoverability, this doesn't just mean, can you basically go back and rebuild a system? But do you have things like configuration files? Do you have the right firmware? All of those things. Are those in safe places offline, for example? Adversaries now are going in and wiping all the configs for all your relays in electric systems, for example, so that you have nothing left, because you can see where they store all the passwords to the relays, all the accounts, all the configuration files are stored on someone's, shared drive in a, Active Directory account. And then, of course, how do you fail back safe? When the system is under attack, how do you start shutting down networks? A good example is a vehicle, like a car. We've designed vehicles now, they've got crumple zones on the outside. So when you smash into something, the car absorbs the damage. The engine and drivetrain shear away. The person in the cage is safe. You've got to do that with your networks. How do you have crumple zones and shear away networks so that the core operations can still keep going? So as a defender, you've got some areas that you can leverage. I just picked 4 of them. The identity boundaries are key. Most of these things now are typically identity boundaries. The 2025 attack on your electric system and heat system, they just logged in with default accounts. Stop that. Everywhere, stop that. Go check for that right away if you haven't already. Everything like remote access paths, no credential reuse. This one is actually really common. Service accounts. And things like if anyone uses a break glass account, that should be alerted. You should know about that. These are all simple practices that can be put in place that don't cost a lot, but they can help you on a really, really bad day. Protocol boundaries, as I mentioned, use something like a tap, a one-way direction to feed telemetry out, so the adversary can't even get to that environment. There physically isn't a path to get there, to mess with the logs, or erase the logs, or change the data. Configuration custody, as I mentioned, know where those configurations are. A lot of our OT doesn't have an operating system. It's got firmware and a config, maybe an EEPROM or an FPROM. In those cases, do you have all those components you need to rebuild that environment? Because you've seen, and there's documented history, Russia will just brick the systems. Like you physically go unrack the device, put a new one in, flash it, put the config on, and try to light the system again. That is how you have to just think of daily operations at this point. Engineered fallback, as I mentioned, manual operation modes. Typically when we do crisis scenario examples or crisis workshops, incident response exercises, preparation, the entity is, the operator is typically, well, we'll just go to manual. I'm like, okay, I hear you. How long can you do that? A day? A week? A month? Around the clock, 24/7? Do you provide like housing and food for the people that are working the shifts? If you've got to go send trucks to locations, what does it look like for comms? Are they using cell comms? Are they using sat comms? What does that look like? Real manual operations for longer than about 3 days is extremely difficult. Practice what that feels like. Because otherwise, when they say, we'll go back to manual, everyone in the room will believe them. And that's not something you should do. Try it. See how well that works for you, and then find other solutions. And then independent observability, monitoring that doesn't share infrastructure. You've got to find a way to see what's happening in your environment in a way that the adversary can't affect it. When the adversary comes in now, they're doing everything they can to hide or make it look like there's a problem somewhere else other than where they are. Look here while they steal your wallet. So you've got to have visibility and telemetry that actually gives you the ability to see what's going on that's not touched by the attacker. Cyber-informed engineering is one of the best ways you can do this. This is using engineering principles to support the cyber components. One of the best examples is a water system, just because it's easier to visualize than maybe an electric system. Chlorine is typically one of the most toxic things. We also use some fluoride, other things in the water systems, but chlorine is one of the big ones. And you can typically go into an HMI and you can set the chlorine delivery to, 100 billion parts per million, some insane number, and just think that we're going to dump all the chlorine into the water system. Cyber-informed engineering is a way that when you basically physically design the chlorine delivery, the pipe that delivers the chlorine is tiny, little tiny pipe, because that's all you need. You need very small amounts of chlorine. The pump that pumps the chlorine into the pipe is a very small pump and can only operate at a safe speed. The reservoir that holds the chlorine is very small, so that it cannot dump too much at once, even if the pump or the pipe were to allow it. So when you physically design the system so that it just doesn't matter if the hacker sets some dangerous limits, the system just will not do it because it's designed that way. That's cyber-informed engineering. Things like remote access, some simple remote access timers. I've seen someone put a coffee timer on an inbound remote access connection to a site. And it's a field site, so that with SCADA, they can turn on the coffee timer. It lasts 20 minutes. The vendor has 20 minutes to come in and the timer shuts off, the power shuts off for the device that allows the connection back in. They have to go back and physically turn it back on again. That's one way to guarantee remote access doesn't happen, because the device is powered off unless it's needed. So there's little things like that that you can do that are inexpensive. You can design the system physically so that it's just much harder for the attackers. The goal is to prevent the bad day from becoming an actual disaster. So hygiene first. Get your shit off the internet. Just get everything off the internet you possibly can. You got to minimize that surface area as much as you possibly can. There's everything out there has got default passwords. Honestly, everything out there, vulnerabilities will be discovered in it. It's just a matter of time. So as much as you possibly can, just get it off the internet. Yeah, the water sector breach recently where 5 facilities were hit. The Internal Security Service just released the report last week. But basically, management panels directly accessible from the internet. That's a bad idea. There are inexpensive ways to just not do this. Multi-factor authentication for everything. I mean, most of these attacks would have been prevented even if they had default credentials with multi-factor authentication, right? It's a good thing to do. It's not always easy to implement, but where you can, do it. Where you cannot, just do you need the remote access? I know some that just have taken it out. They just send a truck. It's just safer. Kill default and reuse credentials. Anything that came with the manufacturer, if you haven't reset that, then expect to be hacked if you're not already hacked. And then, of course, end implicit trust between field sites, field site to field site, field site to dispatch, dispatch to upstream. All of those things should operate where, in order to connect to us, there has to be some degree of trust in that relationship, and everything that we do is explicitly limited to only what is necessary. Deny everything else. So that implicit trust of just an open pipe between connections because you think you're behind some boundary, that's got to go away. And most of the time you can do this within 3 months or less, really. All of these things can be done for most operations procedurally within 3 months or less. So how do you get to things like advanced containment? You want to engineer the blast radius before you need it. This is the cyber-informed engineering. What would a bad day look like? How do I make that less of a bad day? How do I make the problem contained to just this area or that area? And honestly, if it's there, I can cut that area off if I need to. So you have to design this intentionally versus just hope that you get it right. So segmenting operational networks, we've been talking about this for years. It's not done as much as we would like to see. Enforce those boundaries, and then log for recovery. Logging for recovery basically means get as much data as you can, turn on as much logging as you can in that environment, but just make sure it's shipped out of that environment so you can reconstruct things. One of the problems with the recent Iberian blackout in Spain, we could not get some of the organizations to actually give the data. Some of them just didn't have logs. They just didn't turn on logging. So we couldn't reconstruct exactly what happened because we've got missing data, we've got missing logs. Get as much of it as you can, but keep those logs safe. I mean, I'm sure Marchen would love it if there's another problem and you've got really good logs for them to reconstruct what happened and hopefully make this not happen again from the adversary. Treat vendor remote access as high-risk privilege as always. Most of the times we're allowing access in, it's because the vendor needs it. They have legitimate reasons, I understand. But we've got to treat that as high-risk access. Most of the attacks that have come from vendors have been really, really bad. The vendor trusted connections, and there's been several of them as of late, and these go back even to the early 2000s, where a vendor connection was the cause of multiple different client breaches, multiple different site breaches, asset breaches, because the vendor had a connection into the back end. And these have been in power systems, it's been in oil systems, I've even seen it in aviation, and I've seen it in rail and shipping as well, where just a vendor connection allowed multiple different companies to get compromised because the vendor had access to all of them. Monitor all the behavior. This isn't just about is system A talking to system B. Is system B talking to system C? It's when do they talk? What do they say? Is this different? And this is the system behavior. Now the human behavior. Let's say Patrick logged into a console out in the field, but I just badged into the headquarters. I can't physically be in those two places at the same time. So if you're monitoring both system behavior and human behavior, your capability to detect problems goes up significantly. The reason you want to do this primarily is the new adversaries live off the land. They don't break in, they log in. Once they're in, they sit there quietly and they watch what you do. They see how you behave. And then they do the same things with your administrative tools. They don't drop payloads. They don't create new tools. They use your existing tools with your credentials the same time of day you would to cause problems. They want to hide in plain sight. So monitoring behavior is one of the only ways you're going to detect one of these adversaries. Something is different. You won't know what different is if you don't know what normal is. Apply least trust to identities and machine actions. There should be no open trust for anything. As much as you can get to zero trust, it's challenging in OT. I get it. If you just say it's too hard and you give up, that's not the right approach. Do as much as you can. Kill switches and physical isolation paths. I know some that literally have like push button SCADA that will drop the physical connection. It powers off the firewall. It powers off the router. That way they know for a fact it's down. That's the physical kill switch to some of these things. Just in case the adversary has compromised the management plane and you think you shut down the interface, they're just going to re-enable it and you're not going to see the log. So physically disabling the device actually does a much better job. And then, of course, deploying canary mechanisms. Marchen talked about it yesterday. One of the ways they detected this was a canary mechanism said, hey, this is a problem. So as much as you can get monitoring in place, detection components, I've even seen like, flag files or, intentional things that if someone is using this, you'll see it. Plant those things wherever you can. Many times these are, they're not like watering holes or honey nets, for example. These are just simple things that you can use that are canary flags. They're not necessarily like another system that could get compromised, because even things like honeypots can get compromised and used against you. And then this is the key thing. This order is absolutely important. Engineer for containment first. Like, how do I contain the problem? Because operations and availability comes before everything else in our world. How do I contain this and keep it small? Then, how do I recover that small thing, that small problem that I've contained? And then last is, how do I detect if it's gotten beyond what I've decided for containment? So that order is actually the most important thing we've seen from multiple different attacks so far and problems. Recovery is a target. One of the reasons recovery is last is because that's the first thing they do. They don't just want to come in and take you down. They want to come in, take you down, and keep you down. That's the goal. It's not just to cause the harm, but it's to make the harm last. So the fact that you think, well, we can just recover, no, that's one of the first places they go. That's like literally one of the first places they go, is to take out recovery. And they'll take out everything along the way, but they'll take it all out, and then they'll start backing up and bricking things on the way out the door, so that you just absolutely physically can't recover, but any files you might need to replace with devices are also gone. And restoration is now how they measure success in a lot of cases, is how long does it take you to come back from the attack? That's how they measure their success. Supplier risk, I come from the US. Everybody has supplier risks. Buying technology from China, that's a problem. Buying technology from the US, also a problem, right? Risk comes from everywhere. Just act with that as your basic assumption. Every possible place may have supplier risk. Made in means assembled in. We're all buying global components and reassembling with some sticker on the outside that says, made somewhere. Main thing is isolate those higher risk devices, restrict them, identity and privilege for all vendor access. If you can get things like a software bill of materials, great. Especially do this for firmware, because a lot of our devices I mentioned are firmware and config. We're not getting full software bill of materials. And then, of course, if they have signatures for your firmware, verify it before you apply it. The attacker is trying to find ways to get into the embedded firmware so that you just apply it across your system at that level. Now, the cyber-physical reality is we actually deal with this. The systems we touch make real things in the world happen. You click on a screen and a valve opens. You click on a screen and a breaker opens. You click on a screen and an arm moves and boxes go down a different belt. We directly interface with the real world with our physical components. Key thing is, everything made today is digital. You cannot buy analog equipment anymore, period. I come from that world. I know what it looks like. Everything is digital now. You are now a digital company with a product problem. If you're an electric company, you're a data company with a poles and wires problem. If you're a water company, you're a data company with a pumps and valves problem. You can't operate without it. That is now the assumption. Your threats are going to be focusing on things like legitimate access. They don't break in, they log in. Security has to operate at the same speed as failure. You have to be able to contain it as fast as it's spreading. And then resilience is measured by how much you can absorb the attack and keep on going. That is what we need for our world going forward. Estonia's release was one of the best ones. Not time for panic, but definitely time for vigilance. So last thing, common patterns that I'm seeing. There are different triggers that are causing the same weaknesses. We're seeing common mode failures from a lot of the same problems are happening from all these different vectors that are happening. So whether it's wildfire, I've seen earthquake, I've seen tsunami, and I've seen attack hackers, and a lot of the same problems happen the same way. Failure spreads through these flat or wide open trust environments. We've got a lot of that in our space. We've got to try to engineer away from that. The existing visibility and logging just doesn't prevent escalation. We cannot see what happened and reconstruct it. We can't see them coming. We don't have enough visibility to know where to contain, how to contain. So you have to design that ahead of time. In most cases, the root cause isn't malware. It's not even hardware failures. It's typically architecture problems. You just designed the system in a way that made it easier for the attacker. And we did that because that's what we thought was the right thing to do. It was. It's not now. So whether failure is accidental, adversarial, prepositioned, it spreads when complex systems are built on implicit trust instead of engineered control boundaries. Design the boundaries in place. Closing thoughts. Okay. Failures are going to happen. This is going to happen. We do this every day. Attacks are definitely going to happen. Automation is going to misbehave. We're automating more and more and more things. There's the automation paradox where the greater the degree of automation, the more critical the human action becomes because of the cascading downstream effects. So as we automate more, we're going to start trusting this. And I've heard human in the loop a million times. Let's just say we do that. And we put a human in the loop for, we're going to, like it or not, as much as I don't like this, I agree with you, we are going to start to see AI in OT. This doesn't feel good for many people. And it's going to start out, we're going to say, put a human in the loop. That'll solve the problem. We're going to put a human in the loop. The engineer is going to be there to see the sequence. Some telemetry will come in, you'll get an auto-armed sequence, it'll present the sequence to the operator, and the operator will go, okay, looks good, go ahead. That's going to happen 100 times, and it's going to be fine. It'll be great 100 times. It's going to happen 1,000 times. The 1,001, the operator is not going to look, and they're going to click OK. Expecting the human in the loop to be the solution will fail, because humans will fail. We are creatures of habit. These problems will occur whether we like it or not. We're going to end up automating far more of this and less humans in the loop over time. So we will actually grow to trust this. As much, and as I hate to say that and as uncomfortable as it makes me feel, but this is going to happen. As we design these systems, we have to design them so that the failure cannot spread. That's the trick, is whether this kind of problem gets beyond small contained things. So if you design it with resilience in mind, containment is actually possible. Plan to operate without your vendors. I mean, those that have been through real incidents know what this looks like. Vendors get there late. Yes, SLAs get broken. That's a piece of paper, it's a contract. If the day is really, really bad, it's probably not just bad for you. It's really difficult for a vendor to scale when the spread is bigger than just one location. So plan to operate without your vendors. And that's not making the vendors a bad thing. That's just reality, right? This just does not fit a large scale problem. Plan to operate without your telecom. That's one of the first things they do is disable comms. So can you do things like manual operations without comms? How do you do that? Plan to operate with an adversary inside trying to make your life harder. Because that's what they're doing. They're not just going to come inside and say, oh, sorry, you caught us. We'll go away. No, they're going to come in and you're going to detect them and they're going to move. They're going to smoke bomb over here and they're going to embed in this system and hide for a little while you go look over there. So with an adversary in your environment intentionally trying to make your life harder, you have to plan for that. You have to design for that and operate with that in mind. This is what the adversaries do now. And the choice, again, is not to replace risk. You can't just buy new technology and the problem goes away. It doesn't work. You actually have to design it into the system, build it into the way you do business, and you can't just accept the risk because the adversary will take advantage of that. They're already doing that right now, as we've seen. And then, of course, the choice is unmanaged risk or engineered resilience. You literally have those two choices. You can let it run unmanaged, or you can design it so that you know what the blast radius is and test it.